Hello, guys. This is homework number 15. It's just going to be a quick one because we just realized we didn't have the link for this. So I'm just doing this really quick. I'm going to go ahead now and share this homework so we can see what's going on. So I think you guys can see this. This is the first problem on homework 15. Focus on concept question 01 says the first law of thermodynamics states that the change delta U in the internal energy of a system is given by delta U equals Q minus W is internal heat minus work done, where Q is the heat and W is the work. Both Q and W can be positive or negative numbers. Q is a positive number if dash and W is a positive number if dash. And the correct one option here is A. Q is a positive number if the system gains heat, and W is a positive number if work is done by the system. So if the system loses heat, Q becomes negative. If work is done on the system, W becomes negative. So A is the correct answer. Then we'll have focus on concept question 04. The drawing shows the expansion of three ideal gases. Rank the gases according to the work they do, largest to smallest. So this pressure volume graph. So we're going to take the area under the curve. Excuse me. So this has four boxes. This has four boxes, and this has one, two. This one has a little less than four boxes. So it says, so the correct answer is going to be 2, option 2. A and B are tied because they have 4 boxes each, so they have the same area, and they are both larger than C. So the area of C is smallest. So the correct option is A and B a tie, and the smallest one C. Focus on concept question 05 says a gas expands according to the pressure volume graph shown in the drawing. How much work is done by the gas in going from A to B? Be sure to include the correct algebraic sign. So we're going from A to B. So it's going to be the area under here plus the area under here. Okay. And if we take that area under here, it's a half area of this trapezium plus area of this rectangle from here to here. Or you can do area of this triangle plus area of this rectangle plus area of this rectangle. So when you do this as a trapezium, it's half long side plus short side times height. So the long side is 4, the short side is 2, the height is 0.6 minus 0.3, which is 0.3. And don't forget the 10 to the power 5 here. Plus area of this rectangle, 0.75 minus 0.6, 0.15 times the length 2. And when you do that, you get 120,000 joules. Okay. Okay. Next here is focus on concept question 08. It says an ideal monoatomic gas expands isothermally from A to B, as the graph shows. What can be said about this process? So the ideal gas for an isothermal expansion, is that okay? So it means that the temperature is the same. So there's no change in Q, no change in internal energy of the gas. So the V, the 5, the 5th option here becomes the correct answer. Number 5, question, focus on concept question 10, slide 5, I meant to say, a monoatomic ideal gas is thermally insulated, so no heat can flow between it and its surroundings. Is it possible for the temperature of the gas to rise? Yes. The correct answer is yes, the temperature can rise if work is done on the gas physically. So if you compress the gas with something without having to add temperature or something, okay, you can still do work on the gas. So then chapter 15, problem 03 says a system does 185 joules of work on its environment. Is that okay? And gains 80.5 joules of heat in the process. Okay, so we have our convention that Q is positive, the system does work. So W is also positive according to our convention. So applying the first law of thermodynamics, we're going to have delta U is Q minus W. I'm going to have Q 80.5 joules minus W minus 185, and you get minus 104.5 joules. So indicating a decrease. Is that okay? So the system gains heat. So Q is positive. So we're going to have a decrease in the internal energy. Okay, so since you are doing work, you're going to lose some of the internal energy. So the change in internal energy of the environment is the opposite of that of the system. So it just becomes a positive 104.5, is that okay? You know, subtracted from this one here. Yeah, it's just minus that. So it's just an approximation here. 104.5 is 105, so it's just an approximation here. So you could do negative plus 104.5 or plus 105 here to get the same answer. Okay. Chapter 15, problem 06 says 3 moles of an ideal monatomic gas are at the temperature of 343 Kelvin. Then 2526 joules of heat is added to the gas, and 849 joules of work is done on it. What is the final temperature of the gas? So we're going to use the change in internal energy for monatomic gas given by U final minus U initial, delta U equals 3/2 NR T final minus T initial. And then we'll solve for T final here to get this guy. And then we substitute for delta U from the first law of thermodynamics, delta U equals Q minus W. And then we use this expression to put in here. And then we solve for the problem. Is that okay? But we have 2526 of heat added to the gas, okay? And then 89 of 49 joules work done on the gas. So we're going to have negative for work done on the gas here. That's why I have a minus sign here. And then we're going to put all this together to get the temperature needed. Okay. Next, chapter 15, problem 17 says the pressure of a gas remains constant while the temperature, volume, and internal energy of the gas increase by 52 degrees Celsius. 1.96 times 10 to the minus 3 meter cube and 927 joules respectively. The mass of the gas is 21.3 grams and its specific capacity at constant pressure is 1060 joules per kilogram per degree Celsius. Determine the pressure. So a pressure is work done over change in volume, but we know work done is Q minus change in internal heat from the first law of thermodynamics. So we're going to put that in here. And then we can also write Q as mass times specific capacity times temperature change. Then we'll put that in here for Q. And then we'll have this long expression. We put the specific capacity times the mass multiply times 10 to the power negative 3 to change to kilograms times the degree Celsius change minus the change in internal energy given 927 joules divided by the change in volume given, and then we get our pressure in Pascal. Okay, so you just substitute for W and substitute for Q after substituting for W, and then you get your answer. Okay, we'll go to the next one here. Chapter 15, problem 21 says, suppose 4.95 moles of a monatomic ideal gas expand adiabatically and its temperature decreases from 390 to 243 Kelvin. Determine the work done, including the algebraic sign by the gas and the change in its internal energy. So the work done by the expanding gas is 3/2 NR T initial minus T final. So we're going to put that in here by converting. Okay, these guys are already given in Kelvin, sorry, so we don't need to convert. And then we get these joules. And then the change in internal energy, so it's an adiabatic process, so Q equals 0. So change in internal energy is just minus W from the first law of thermodynamics, so it's just going to be negative of that one. Okay. Then chapter 15, problem 22 go says 3 moles of neon expand isothermally from 0.182 meter cubed to 0.303 meter cubed, while 4.92 times 10 to the 3 joules of heat flows into the gas. Assuming that neon is an ideal gas, find its temperature. So for an ideal gas, work done is nRT, the natural logarithm of final volume over initial volume. So from here, we solve for T to be W over NR logarithm, natural logarithm, or you say ln of V final over V initial. So del U equals 0 for isothermal expansion. So that W is equals just Q. And then we just put Q up here, and then the other things in the denominator stay the same. And we put them, final volume, initial volume, R is the constant, 8.31 joules per mole per Kelvin. And we get our answer for the final temperature, the temperature T. Chapter 15, problem 23 is the next, and it says, the temperature of a monoatomic ideal gas remains constant during a process in which 2450 joules of heat flows out of the gas. How much work, including the proper plus or minus sign, is done? So Q is negative 2450 since system is losing heat, it flows out of the gas, and delta U is 0 since there is no change in internal energy. The temperature remains constant. Okay. Then The net work done during the isothermal process is Q minus delta W. So we just have negative that plus 0 minus 22550 joules. So it's just negative of the energy that was flowing out of the gas. So the negative sign indicates that work is done on the system. Chapter 15, problem 28 is the next problem. It says a monatomic ideal gas expands from point A to point B along the path shown in the drawing. Determine the work done by the gas. That's problem A. Determine the temperature. The temperature of the gas at point A is 204 Kelvin. And then we are asked what is the temperature at point B. Then the last problem, how much heat has been added or removed from the gas during the process. So let's look at the first one. So from the drawing, we see under the curve, we have 5 squares, 1, 2, 3, 4. These two merge together as one. So where each square has an area of 2 times 2 times 10 to the 5, 4 times 10 to the 5 joules. There's 2 here, the box, 2 for the meter cube volume part, 2 for the pressure times 10 to the 5. So work done by the gas is 5 squares times each area of each square, which is 2 times 10 to the 6. Is that okay? That's 5 times 4 is 20 times 10 to the 5. That's 2 times 10 to the 6 joules. That's the answer for A. Then we have that PAVA over TA is PBVB over TB. Then solving for TB and using the fact that PA equals PB according to the graph, pressure at A is pressure at B, and taking values for VB and VA from the graph. So from here, TB is PBVB times TA divided by PAVA when you solve for TB from here, and which is VB over VA because PA and PB are equal according to the graph. Pressure at A and pressure at B are the same. So those cancel out. So I just have VB over VA times TA, and then I just get V of B, the volume of B at that point, 10 over V of A, 2 times the temperature is given in the problem to be 204 Kelvin. So from there, I get the temperature at B. Now let's go to the C part of the problem. And then from the reasoning section, we know of just from looking at the problem, I don't have the reasoning section here, but the heat Q that has been added or removed from the gas is given by Q equals delta U plus W. So the change in internal energy of the gas is UB minus UA, which is 3 over 2 NR TB minus TA. So we can calculate that. So Q is delta U plus W. So delta U is this equation right here plus W. So we now use the ideal gas law, PV equals nRT, to replace nRTB, because we have nRTB minus nRTA. So it just give me PBVB minus PAVA here, using PV's nRT in this part of the problem. Then plus W still stays. So it becomes 3 over 2. Instead of nRTB, I have PBVB minus nRTA becomes PAVA. Then taking the values of PBVB, PAVA from the graph, and using the result of W we got from part A, then we find that the heat is Q equals this times that minus this times that plus that, and we get 4.4 times 10 to the 6 joules. So it's just a substitution thing right here to get the final answer. Okay, focus on concept question 13 is next. It says a heat engine takes heat QH from a hot reservoir and uses part of this energy to perform work W. So assuming QH cannot be changed, how can the efficiency of the engine be improved? So how can the efficiency of this engine be improved? You have to increase the work, W, then the heat QC rejected to the cold reservoir will decrease because this is constant. So you can only increase this guy and decrease this guy to have high efficiency. So you want to do more work than lose heat, okay, to the cold reservoir. So C is the correct answer in this case. And we're going to see in this next example, focus on concept question 15. The 3 Carnot engines shown in drawing operate with hot and cold reservoirs whose temperature differences are 100 Kelvin. Rank the efficiencies of the engines largest to smallest. So 900 minus 800 is 100, 500 minus 400 is 100, 200 minus 100 is 100, but they don't have the same efficiencies because this guy is only losing half of its temperature to the cold reservoir from the hot reservoir. The other half is gone, 50% is gone to work done. But this guy is losing almost everything to the cold reservoir and only 1/5 of the initial temperature in the hot reservoir going to work done. So this one has half going to work done, this one has 1/5, and this one has like 1/9 going to work done. So C is the one with the highest efficiency, followed by B, followed by A. So the correct answer is 3 right here. Okay. So it just depends on, it doesn't mean the temperature difference doesn't matter. It's how much of the total incoming in the hot reservoir is going to work done that determines the efficiency that you should have. The next is focused on concept, question 17. It says a refrigerator operates for a certain time and the work done by the electrical energy during this time is 1000 joules. What can be said about the heat delivered to the room containing the refrigerator? So if it's doing a work done of 1000 joules, so the heat delivered must be greater than 1000. It's like the one coming from the hot reservoir. So the hot reservoir must be higher than the work you see, because you need to have some going to the cold reservoir. So A is the correct answer in this case. Next is focus on concept, question 20, and it says 600 joules of heat is added reversibly to a gas whose initial temperature is 300 Kelvin. If the gas expands isothermally, what is the change in entropy? So entropy is number of joules per Kelvin in this case. So 600, just put this in numbers and it's easy. Joules per Kelvin, 600 divided by 300 Kelvin, joules divided by Kelvin, so it becomes 2 joules per Kelvin in this case. So the correct answer is E. Next, chapter 15, problem 44 says, an engine has an efficiency of 64% and produces 5,500 joules of work. What are the input heat and rejected heat? So we're going to get that efficiency is work over Q hot, or Q hot is work over efficiency. We get that. So this is going to be the magnitude of the input heat from the hot reservoir. And then we know that Q hot is work done plus Q cold. So Q cold in the cold reservoir is Q hot minus work done. So it's going to be 8,600 joules that we have minus the work done that's given right here. So we have the heat rejected as the one going to the Q cold. So heat input is 8,600, heat rejected is 3,100, using these two equations separately, and the correct answer becomes B. The next problem, chapter 15, problem 53 says, a Carnot engine has an efficiency of 0.856 and the temperature of its cold reservoir is 382 Kelvin. Determine the temperature of its hot reservoir. And if 60-70 joules of heat is rejected to the cold reservoir, what amount of heat is put into the engine? So efficiency is 1 minus temperature at cold reservoir divided by temperature at hot reservoir. So we can get temperature at hot reservoir to be temperature at cold reservoir over 1 minus efficiency. And then we put that here with this values we're given, we get this Kelvin. And then solving for QH from here, this other equation, we get QH is QC times TH over TC, and then we just solve for the heat coming from QH giving QC, the heat rejected to the cold reservoir. Okay. So we're going to use this temperature from hot reservoir from A part to solve this B part. Very important. And then chapter 15, problem 64, go. The inside of a Carnot refrigerator is maintained at a temperature of 277 Kelvin, while the temperature in the kitchen is 302 Kelvin. Using 398 joules of work, how much heat can this refrigerator remove from its inside compartment? So solving QC over QH equals TC over TH. So we have QH equals that. Then QH is QH minus, QC is QH minus W. So we're going to put that here. This is QH minus W to give me QC. We solve this for QH from this equation. Then QC is QH minus W. I put this for QH here minus W. Then QC becomes from here W over TH over TC minus 1. So this is what I'm solving for QC. W, the work done, removed over TH over minus TC minus 1. Over TC minus 1. And that solves the problem here. Okay. So the hot reservoir is the 302 temperature in the kitchen, and the cold reservoir is the Carnot refrigerator minus 277 Kelvin TC. TH is 302, TC is 277. TH is the hotter one, TC is the colder one, and then minus 1. The next problem says, chapter 15, problem 65, a refrigerator operates between temperatures 294 and 273 Kelvin. What would be its maximum coefficient of performance? So coefficient of performance is 1 over Q hot minus Q cold minus 1. But we have Q hot over Q cold is T hot over T cold. So this becomes T hot over T cold minus 1, since Q hot over Q cold is the same as T hot over T cold. And then that becomes 1 over 294 divided by 273 minus 1. And that gives us our answer for the coefficient of performance. The next problem is chapter 15, problem 67. It says the water in a deep underground well is used as the cold reservoir for Carnot heat pump that maintains the temperature of a house at 309 Kelvin to deposit 12,600 joules of heat in the house. The heat pump requires 748 joules of work. Determine the temperature of the well water. So QC equals QH minus W. So QH is given minus W is given, then TC is TH times QC over QH, and that solves the problem to get the temperature of the well water, the cold reservoir temperature, basically. Then we have the last, the one before the last problem, and it says, find the change in entropy of the water molecules when 2.65 kilograms of ice melt into water at 273 Kelvin, and 2.44 kilograms of water changes into steam at 373 Kelvin. So, so if we imagine a reversible process in which 2.65 kilograms of ice melts into water at 273 Kelvin, the change in entropy of the water molecules is Q over T, so which is mass times the liquid of fusion, specific heats of fusion of the water, of the ice, times divided by the temperature. So we use that here. This is a constant that should be given in the book. It's not given in the problem. Heats of fusion or melting of ice. And then we got that here. And then for the B part, the same thing, heat of vaporization for the water into steam using the mass of the water right here, water molecules. And you just get the same thing here for the entropy here and the entropy here, just changing heat of fusion and heat of vaporization. And the mass is given separately for those. The temperature stays 273 for melting, 373 for boiling or vaporizing. Okay. Okay. Next, the last problem, chapter 15, problem 78, go. On a cold day, 25,900 joules of heat leaks out of a house. The inside temperature is 20 degrees Celsius and the outside temperature is negative 22 degrees Celsius. So what is the increase in entropy of the universe that this heat loss produces? So heat lost from the reservoir inside the house, the change in entropy is negative. So delta S entropy H is minus Q hot over T hot. So since heat is gained by the cold reservoir, the outdoors, the change in entropy is positive. So the change in entropy for the cold reservoir is plus Q cold over T cold. So so Q hot and Q cold represent the magnitude of the heat. And then the change in entropy of the universe is sum of change in cold plus change in hot reservoirs. So QC over TC. Then we have minus, because that one is the change in temperature inside the house. The heat is losing from it, so we'll have a minus in that one. Minus QH over TH, and this is the key to solving the problem. And you get that. Okay. So we're going to use TC in Kelvin, 273 minus 22, and then T hot, 273 plus 20. That's how we got the values we use here, TC and T hot. 251 Kelvin for TC and 293 Kelvin for T hot. And you get this answer. So your values might be different for your problems, but the steps are the same. Substitute your values, put the constants where you have them, work the problem carefully, and you get the correct answers. Thank you, guys. And hopefully I'll see you again next semester, or if you're taking any other physics class. Have a good one.